Okay, I just received the signal from our coordinator for this event that I can go ahead and get started. So let me say welcome to all of you. It looks like we've got most of 100 people already here, and I know the attendee list is bigger than that. There's people tuning in from all over the world, so thank you for that. Some of you I know, most of you I don't. Just as a very brief introduction, I'm Steve Brower. I've worked at Morgan Schaffer for 18 years now, and in my time here, I've spent most of my time leading the development of DGA monitoring products, both online monitors and portable analyzers. So that's me. And I'm very happy to be here presenting at this webinar in collaboration with my colleagues at Altanova. For those of you who don't know much about Altanova, it's a company with a long-standing excellent reputation for providing diagnostic test equipment and monitoring equipment for all kinds of different electrical assets. And so I invite you to, if you don't know them, familiarize yourself with their website. Before we begin, just a couple of sort of administrative topics. The first is that I hope as we go, you may have some questions about the slides. That'd be great. I think it's best that I wait until the end of the presentation and answer the questions then, just so I keep respecting the total time we have here today. Please type your questions into the chat. I'll try to answer as many as we can at the end. And if by chance I don't have time to answer all your questions, I will come back to you with an email in a couple of days following the webinar here. So, and the other administrative thing is I'm told that all the attendees will receive a recording or a link to a recording of today's event, so you can review it afterward. Okay, so let me plunge right in. We're going to focus today about DGA monitoring specifically, and some of the technologies that are used in the solutions that are available in the market today, as well as some of the things we've learned working with our customers over the years to build up successful DGA monitoring programs in all parts of the world, really. So let me advance the slide if I can. There we go. So you may realize, and for me it's impressive to think how we've been doing DGA on transformers for over 50 years now. And in that time, the methods of DGA have, of course, improved tremendously, both for making the measurements and for understanding what they mean. And I think it's a fair statement today to say that DGA has become the most powerful tool that we have available for understanding the health of an operating transformer. And most of this history, of course, has been built up using laboratory DGA, using syringe samples. What I'm going to focus more on today is online DGA, rather. And it brings a number of key benefits, which I want to talk briefly about here. And the first one really is that a lot can happen over the course of a year between your annual laboratory samples. And so doing online DGA, of course, brings the advantage of being able to identify faults that may emerge sooner than you would if you were just using laboratory approach. So by finding faults earlier, it gives you time to understand them, do other tests, and plan a course of action. And all of that is to reduce the cost of repairing whatever is the root cause. So that's, of course, maybe the biggest advantage of doing online DGA. But also, it can help you keep gassing units in service. If there's a unit you know is having some issues and you want to make sure it doesn't get worse as you continue operating it. Another application is just during those peak periods of the year when you know that the transformers will be running at maximum their capacity or maximum of their annual cycle, you can keep an eye on them and make sure that they're behaving well. And the last thing I'd like to mention is that this is becoming, I think, increasingly popular in different parts of the world, where people are deploying large numbers of DGA monitors on a whole fleet of transformers and pulling all that data back into a software tool that allows them to automatically assess the health of each unit in the fleet, and with that information to prioritize maintenance across the fleet. So we call this, of course, condition-based monitoring, or condition-based maintenance, rather. So I will be talking a lot about the different gas measurement technologies in DGA monitors on the market today. But before doing so, I want to just a reminder that although the gas measurement system is a key subsystem, of course, in these products, there are lots of other subsystems that also play a really important role in determining the data quality, the reliability, and even ultimately the cost of ownership for a fleet of monitors. And some of them are listed here. I'll talk about some of these as we go through. Just a reminder that these systems are as important in some ways as the gas measurement system itself. So yeah, I'd like to start with the basics. We'll start simple with the 1 and 2 gas monitors. These typically measure hydrogen in the oil because the great majority of transformer faults will generate hydrogen. Some of them also can measure and report carbon monoxide, which can be associated with faults affecting the cellulose insulation. And the purpose of these type of monitors is really fault detection. They can't help diagnose exactly what kind of fault is going on. So their role is really to detect as early as possible a changing condition that's generating gases. And there are 4 different types of gas measurement technologies in the industry today in these kind of fault detection monitors. And I've made a list of them here for your reference. 3 of them require a gas extraction membrane. One of them, the last one, which is a hydrogen variable resistor, it works directly in the oil. And they each have some pros and cons. But the one I'm going to focus on here today is the one that I think is the best suited for the challenge of early fault detection. And these monitors use thermal conductivity detectors to measure the hydrogen and also the carbon monoxide in some cases. And I think they're the best for early fault detection because they're the most sensitive. They're actually an order of magnitude more sensitive than other solutions. And they're also extremely stable over many, many years. So that means that a very small change in hydrogen concentration, even if it's years down the road, these systems are really good at picking that up. And they're also the most accurate. They can be, oftentimes they benchmark very well against the DGA lab. And a little bit how the technology works here is very simple. There's a small glass bead thermistor. A thermistor is a temperature variable resistor, as you may know. And so we have this tiny bead that's less than 1 millimeter in diameter, suspended on some fine wires in a cavity filled with the gas that we've extracted from the transformer. And we pass a small current through this thermistor to heat it up. And it turns out that if the gas around that thermistor is more thermally conductive, that is, if it contains more hydrogen, that thermistor will reach a lower temperature because it's conducting heat effectively through that hydrogen in the gas. So hydrogen is anomalously a conductive gas. It's 3 times more conductive than the other gases in this application. So it gives us a leverage on detecting the presence of the hydrogen in the gas. We layer on top of this a number of other tricks in order to carefully isolate exactly the hydrogen and the carbon monoxide signatures. And I always like to present a case study or two. So this was a transformer down in Texas. It was coming up on springtime, so it was late in May, and it was warming up outside. Temperatures were rising. And if you look on the bottom of the image here, there's a plot of the oil temperature in that transformer over the course of about 2 weeks. And over that time, the daily cycles were modest at first, and then they started growing as everyone was switching on their air conditioning and the transformer was being loaded more heavily during the day. And around the second day, around the 26th of May, we started seeing hydrogen and to some extent carbon monoxide being generated. So a fault had emerged. It was being detected by this TCD fault detection monitor. And it progressed for a course of a week or two. And tragically, what happened is the transformer failed. And the first time we saw this data was after we were cleaning up after the transformer failure. So the main lesson I want to share with you from this example is maybe two things. First of all, very sensitive hydrogen detector there. We could have detected, when the concentration reached 5 ppm, maybe 10 ppm above a historical baseline of 0. Unfortunately, the user of this monitor did not set their automatic gas alarm levels at the optimal place. So I think they had actually left the factory default settings, which were in the hundreds of ppm. So the main first lesson, I think, of this whole presentation today is, in order to ensure a good return on investment of a monitoring program, it's really, really important to set the gas alarm levels in the monitor based on the history of readings on that specific transformer. And I'll maybe come back to that point again later on. So when I think of the critical performance specifications for DGA monitors in general, as I mentioned, sensitivity is important for early fault detection. And the other parameter that's really essential is what we call accuracy in service. So this is accuracy in service. What I mean by that is, if you look at the readings coming out of the DGA monitor, how well do they compare with a good DGA lab? And the advantage of a monitor that's accurate enough to agree with the lab is that at any point in the year, you can understand if there's a fault, and more than that, what kind of fault it is. And if it's a severe fault, you can actually classify the fault if you've got good enough accuracy from your monitor. It's also fair to say that if the monitor does closely agree with a good DGA lab consistently, it will work well for early fault detection as well, because labs are very sensitive in themselves. And the other big advantage to having an accurate monitor is to avoid false alarms. False alarms are, unfortunately, they can be very effective at eroding people's confidence in the DGA monitoring program. People on the maintenance team who go out chasing false alarms can get frustrated by that. The management can lose confidence that it's a good investment to have the teams doing that. So a really important feature of a good monitor is that it does not generate false alarms, but rather continues to deliver accurate readings throughout the year. Now, I sometimes get the question, well, how accurate is good enough? And I think the person who made the best progress toward answering this question is probably Michel Duval. He published a paper back in 2005, which I try to summarize a little bit here. You may know that the Duval triangle is a way of looking at 3 different fault gases and plotting them up in this triangle form. And depending on where we find ourselves in the triangle, it represents a different type of fault classification that's going on in the transformer. And what Michel did in this paper was he said, well, what if I don't know my gas concentrations perfectly, but I have a limited accuracy on them? And so he drew on the triangle what it looks like if your accuracy is, say, only 15%, and those are the red shapes, or if it's bigger, it's like 30%. And what I think the conclusion of all this was that basically, if your accuracy from your monitor or your lab is about 15% or better, there's a very high likelihood that you're going to land in the correct fault zone to correctly understand the nature of the fault. But if the accuracy is poorer than that, if it's 20, 30%, well, maybe the odds are 50-50 that you're in the right zone at doing this kind of analysis. Okay, so now I'm going to change the direction a little bit and start digging into the different gas measurement technologies that are used in multi-gas monitors. Of course, multi-gas monitors, there's more and more of them on the market all the time. They're improving in many ways as we go. So this is just an overall survey, if you wish, of how these technologies work, because I think it's intriguing for many people in the industry. So, and the way I think about this is that there really only are two different ways of measuring the gases in this application. The first one is gas chromatography, which has been used by our labs for over 50 years. And the other way is using some form of infrared absorption spectroscopy, where we take advantage of the fact that different gas species absorb infrared light in certain characteristic wavelengths. So it's really one or the other, and there are advantages to both types, and there are many different varieties of each of these two. There's different types of GC monitors, there's different ways of doing the infrared absorption measurements, but ultimately every monitor is in one of these two categories. I'll start with chromatography, which has the longest history in the industry, of course. Many of you will know this, but the way it works is there's a key component of these systems is a gas separating column, and that's shown as these coils here in the middle of this image. So what we do is we take a small sample of the gas out of the oil, and we propel it down this long, skinny column using a flow of helium gas to push it along. And the inside of that column contains a chemical coating or powder, which has not too strong, not too weak chemical interactions with each of the gas species that are involved here. And the net effect of that is that different species travel through this column at different rates, so that each one reaches a detector at the end of the column at a different point in time. And so that's shown here in this image as these peaks, these blue and red peaks that are coming out. This is meant to indicate the chromatogram, which is the raw data that comes out of a GC. And once a day, it's necessary to calibrate a GC system by injecting a known gas, a calibration gas, through the same system and measuring these peaks for that gas. So we compare our calibration gas to our actual sample at any point to make the accurate readings. Now, a lot of advantages to chromatography. It's the most sensitive technique we have. It's the most accurate one. It's that's why we use it in labs, and that's largely due to the automatic calibration that's done in monitors that use gas chromatography systems. They all have an onboard automatic calibration system using calibration gas. And the other nice advantage to chromatography is the readings are not affected by what I'm going to call interference gases or interference compounds. You may or may not know that in transformers, especially older transformers, there can be other gases and compounds present in the oil different from the ones we measure in DGA. There can be, for example, heavier hydrocarbon gases. There can be SF6 occasionally leaks in from bushing. There can be alcohol, acetone, acids. A whole soup of different things can reside dissolved in the oil. And one of the nice things about the gas chromatography technique is those interfering compounds, they actually don't interfere. They come out of the chromatography column at different points in time. That's what I'm trying to indicate with these red peaks here. Those are the signals from these interfering compounds, and they're in a different location compared to the DGA gases. So they don't introduce a measurement error for a measurement of the target gases. So that's great. It's a fabulous measurement technique. The big downside, of course, is that in order to run a gas chromatography monitor, we need a cylinder of helium gas and we need a cylinder of calibration gas. And there's cost and time associated with managing, changing out those cylinders every 4 years. And not everyone wants to do that. So that's one downside. And the other downside is that some of these models, some models that use gas chromatography, the gas separating column sort of wears out after a period of time, so they need a major overhaul after 4 or 5 years of service. So now I'll change direction and talk about the different ways of doing these infrared measurements I alluded to. Once again, it's useful, I think, to think about the molecular structure of each of the gases that we're trying to quantify. And each molecule, different type of molecule, has different natural vibrational modes as those atoms move around, vibrate within the structure of the molecule. And it turns out that infrared light can be strongly absorbed by a molecule if the frequency of the light is lined up with one of those natural vibrational modes, if it has the same frequency as the natural vibrational frequency inside the molecule. So that's the nature of infrared absorption. And we can detect the absorption in sort of 2 different ways. One is what I call attenuation. That is to say that if you have a light source on one side of the gas and you measure it some distance away, the intensity of the light diminishes as it's being absorbed by the gas. So you measure how the intensity is decreased or attenuated as the light passes through the gas. And the other way is that you can actually measure as the light gets absorbed by the molecule, there's a very small amount of heating. The light gets transformed eventually into heat. And so there's a technique for measuring that heating of the gas, which I'll talk about. One limitation of the infrared measurement methods, however, is that there are certain gases that just simply don't absorb significantly the infrared light. And so monitors that, multi-gas monitors that use these infrared methods, they have to use other sensors, other ways to measure hydrogen, oxygen, and nitrogen, because they don't have any signature in the infrared measurement method. One of the challenges of the infrared techniques in general is the fact that the infrared absorption spectra of all the different gases in this application, they have overlap. There are spectral regions where you have 2 or even 3 gases that are absorbing in the same narrow range of wavelengths. So what this means is that when making these kind of measurements, it's necessary to use some software to untangle those overlapping signals taken at different wavelengths across the spectrum. So in terms of the configurations for doing the IR measurements, I'll start with what I think is probably the simplest one, and it's commonly called the non-dispersive infrared approach. Sometimes you'll hear NDIR. And it is really basically quite simple. You have typically a tube, a volume of the gas in a container in the shape of a tube, similar. You have a light source at one end, and you have 1 or more optical detectors at the other end. And for each detector, there's a filter that's allowing light only from one narrow wavelength. So there's sort of one filter detector pair for each of the target gases we want to quantify in this application. And so, as you can imagine, if there's more gas present of a given absorbing species, there will be more attenuation, and there'll be less of that light reaching that detector as it propagates through the gas. And the filters, they can be either static filters, just fixed optical elements, or there's even a solution out there now that uses a scanning method to make a tunable filter for an NDIR monitor. Some advantages of the NDIR approach is that the hardware can be quite simple and economical. On the downside, it's challenging to make these systems as sensitive as might be needed in the application. There are tricks to improve that. Like all the IR methods, because of these overlaps that I talked about in the spectra, when there are interfering gases and compounds present in the oil, that can lead to inaccuracy in the readings. So that's a challenge in general for the IR methods. And some models have been known to drift lose their accuracy slowly over time. The next IR measurement method that is used in the industry, there is a DGA monitor using this approach, is what's called Fourier Transform IR Spectroscopy, FTIR. And this is kind of the big brother of the NDIR that I just presented. It has some things in common. Again, there's a long cylindrical gas sample, and there's a light source on one end and some light detection system at the other end. The big difference here, though, is the nature of the light source, which is not just a white polychromatic light source, and it's not a narrow light source. It's a tunable light source, and it's tuned using a system called an interferometer. So what an interferometer generates is a beam of light that contains a series of wavelengths, a harmonic series of wavelengths. So for any position of the interferometer, we're shining a harmonic series of wavelengths of light through the sample, and the signals are being recorded by this light detector at the other end. And then the interferometer is tuned to scan a whole range of central wavelengths and build up a whole bunch of data with different interferometer settings. And it turns out, smart people who developed this technique figured out that if you perform a Fourier transform calculation on the data that's accumulated with this type of optical configuration, you can recreate with good resolution the infrared absorption spectrum of all the gases that are in the sample. So it's a very clever technique and quite new on our market. Some of the advantages, I think the biggest advantage is that we accumulate here a much more complete spectrum. There's a lot more spectral information you can be gathering with this type of approach. And that is helpful, for example, if there are, again, these interfering compounds in the oil, you can do a better job of identifying them in the spectrum and compensating for them, pulling them out of the data and getting good measurements of the target gases for the DGA. Maybe the biggest downside for these systems, I would say, though, is that they're, you can sort of maybe judge from this photograph, from this sketch rather, they're very complex and there's some delicate optics. So they tend to be a bit expensive because there's a lot of complex optical components that are very precision built and have to be manipulated in very precise ways in order to do the measurement. So that's FTIR. And the last technique I'd like to present here today is the one with the longest history, actually, in our industry. It's called Photoacoustic Spectroscopy. And the way this works is actually, I think it's really interesting. There is a light source, again, an infrared light source. Normally it's a lamp, a filament lamp, that's focused down using a parabolic mirror through a optical chopper. And what the chopper does is it transforms this light beam into light pulses. And those pulses are at an audio frequency. The light then passes through an optical filter. Typically, there are a collection of different optical filters that can be put into position to measure the different gases one at a time. So what ends up being shined into the gas sample is a chopped, filtered beam that's designed to excite one gas at a time from the family of possible gases that could be in the sample. Now, because you've got pulses of IR light entering the gas sample, if they're being absorbed, what that does, as I mentioned before, the absorption creates a little bit of heat. So you get pulsed heating of the gas inside the gas cavity. And pulsed heating leads to pulsed expansion. Right? If you heat a gas, it expands a little bit. So this pulsed expansion of the gas, well, that's basically pressure waves or sound waves. So there are small microphones, very sensitive microphones on the sides typically of the gas cavity that are able to pick up the sound of the IR light being absorbed by the gas. And that's why they call it photoacoustic. Typically, the the chopper is running at an audio frequency, so the microphones can pick it up somewhere in the audio frequency range. And some of these systems have quite elaborate, optimized different shapes of gas cavities in order to maximize the amount of microphone signal for a given quantity of IR light and a given quantity of gas sample. Once again, there are some advantages and disadvantages of this approach. As in all the IR techniques, some models can be compromised in their accuracy if there are interfering gases present in the sample. Adding more IR filters is a way to get more spectral information and to combat that issue. Some models have been known to drift over time, and some need major service after 3 or 4 years of continuous operation. There are, of course, also some advantages. It's intrinsically it's the most sensitive of the techniques, which is important because we're often measuring in very small concentrations in our applications. So for detecting small amounts of emerging gas associated with new faults, having that high sensitivity is an advantage. And I'm happy to be able to share with you today there's a new model on the market using photoacoustic techniques that has a built-in automatic calibration system that helps to compensate against the drift that has been historically an issue with this kind of approach. So let me talk about that here on the next slide. This is a new product developed by my team over the last number of years. We call it the Callisto R9. And the way we like to think about this product is that it combines the best of both worlds. And what I mean by that is that, like other infrared DGA monitors, it doesn't require the use of any gas cylinders, so it makes it easy to install and easy to operate. But on the other hand, like gas chromatography monitors, it actually has an onboard automatic calibration system to ensure that the readings stay accurate throughout the product lifetime. And the way this works, I won't go into the details of it, but basically there's a small reservoir of liquid water in the product. And so the product uses water vapor to perform a calibration regularly through its operation in order to keep the readings accurate like they were at the factory. So it's a very sensitive and very accurate IR monitor. We've got a couple of different patents, 3 different patents related to different innovations that we created along the way. It has all new electronics and software compared to the Callistos we have been selling up until this year. New electronics is helpful in terms of being able to ensure we can deliver the product in a timely way, given all the supply chain challenges that are faced by all kinds of businesses all over the world today. And the new software is it's a web interface that with a Linux-based operating system, and it's great because it allows us to meet the current and evolving requirements for cybersecurity that are becoming increasingly demanding for all kinds of assets that we're installing on the grid. So, and at the same time as having all this new content, the team that developed this has been involved in developing Callistos for most of 20 years. And so there's a lot of lessons learned, a lot of know-how built in based on the other systems that support the gas measurement process itself. So we've been in field trials on this for about 2 years, and it's been going very well in all different climates and different partners. And maybe the last thing I'll mention about the new product, like all of our products, we can provide through Altanova and Doble, we can provide local support in over 90 countries for these products. So I'll go back to talking about now some of the other important pieces of technology that are inside DGA monitors. Just again, a little bit of an overview of how these things work. In all the multi-gas monitors and most of the fault detection monitors, the gases are measured in the gas phase. It means we have to extract the gases from the oil. And for me, there are really 2 different classifications of gas extraction. One is what I call open headspace. What I mean by that is there's somewhere inside the product, there's a container that is partially filled with oil and partially gas space above the oil. And there are different ways of reaching an equilibrium of the gas concentrations in the headspace above that oil. Some of the products use mixing, some of them use a pump to bubble gas through the oil. There's a product that actually pulls on the oil to create a negative pressure in the headspace, a partial vacuum in the headspace. All of these are techniques to encourage the creation of an equilibrium between the oil and the headspace in a timely way, so that measurements can be done in an hourly or so frequency. These techniques require careful control or careful measurement of the volume of gas and the volume of oil. That ratio of those two volumes is a key parameter in the accuracy of the reading. The only thing with these is there is a downside, which is that in that headspace, in that vapor above the oil, there's always a bit of oil vapor, and that oil, the vapor pressure of that oil is there. So there's the possibility with these type of extraction systems that over time oil vapor migrates into the gas measurement system, which is not what you want. Normally you want a gas measurement system to be pristinely clean. So the other way of doing the gas extraction, which is the approach that our products prefer, is what we call a membrane gas extraction. Here, the membrane is most commonly in the form of gas permeable Teflon tubing, thin-walled Teflon tubing that's immersed in the oil. As shown in this image here, in this particular case, there are multiple loops of this tubing that are bent back so that they all exit the oil container at the same point. But there are other configurations as well. Nice thing about membrane gas extraction, there's no moving parts, so they're very reliable. The volume ratios are fixed, so you get very reproducible extraction over time. They're tough. They can withstand vacuum. If you're doing a vacuum tryout on a transformer and you forget to valve off the monitor, it's not a problem. It won't cause any damage to the extraction system. It won't move oil from one place to another either. And the big advantage really for me is that oil and oil vapors can never pass from the extraction vessel into the gas measurement system. And that's important for long-term accuracy and reliability of the gas measurement system, which is true for whether it's a GC measurement system or an IR measurement system. Oil vapors are not conducive to long-term accuracy and reliability. Other important features in the monitor, just a few to mention here. Thermal regulation of the gas extractor and the analyzer is important. These are temperature sensitive processes. Oil flow monitoring, very useful. We've had cases over the years where people accidentally valve off a monitor and they don't realize that for years to come. So it's nice if the monitor can check that the oil is truly flowing through and otherwise report an error condition. And finally, a bubble trap is also a useful feature just to make sure that during installation and during operation, there's no way for gas bubbles that may arise in the monitor and the oil lines. There's no way for those to make it into the main tank oil, where they could cause compromised situation for the dielectric of the transformer. So that was a lot of talk about technology and the different ways of measuring gases and doing the DGA process in the field. I'd like to take just one slide and talk about some other important features of DGA monitors that you're not going to find information about them on the data sheet from the manufacturer, but they play an important role, I think, in choosing a monitor to deploy a successful DGA monitoring program. The first one, I talked a bit about real-life accuracy. Many monitor manufacturers, they talk about accuracy in their spec sheet, but it's accuracy at the factory under ideal conditions. It's not necessarily very representative of how the monitor is going to behave in the field on a real transformer. And so that information is a bit difficult to get your hands on. Reliability is not really discussed on the data sheet. Maintenance requirements in the real life may or may not be obvious from the vendors. Difficult to evaluate how responsive the vendor is going to be if you have a problem with your monitor, or you have a gassing situation on a transformer and you want some guidance and expertise. It's worth to think about if that's the kind of supplier who can provide those kind of services. And the other one, and this comes a lot from talking to customers that have been with us for a long time, they've told us, it's really, in their view, it was important to consider a vendor that is going to be with them for the long haul. I think their perspective has been that if I'm going to buy DGA monitors, I'm going to spend a lot of time and money training people on how to install them and service them, maintain them. Maybe I'll be stocking some spare parts. And I want them to be serving me for 10, 15 years. And so is that vendor really going to be there? And to what extent are they going to be interested and able to support me as I go through these next 10 years with this program? And maybe another way of asking that question would be, how close to their core business is DGA monitoring? Is it a company that's really their main bread and butter, or it's just a piece of a bigger business? So how do we possibly get information about these important questions? Well, there's really only two ways to go as far as I can tell. One is, and many people do this, they buy monitors, they buy a variety of them, they deploy them, and they test them themselves. And that works, and that's great. Another way that's maybe less expensive and can save a lot of time as well is to simply go to conferences, talk to other asset managers and people at other utilities who've been successful in building up DGA monitoring programs, and maybe you'll be able to pick up some tips to save yourself some time and maybe make good decisions early on in your process. Okay, another. This is a good old case study that I like to present, in which it relates to a GC monitor that we deployed on a new transformer. It was a brand new 900 MVA unit somewhere in the southern US a number of years ago. And the story with this was that the owner installed the DGA monitor a few days before they ever first energized this new unit on the pad at the site. So they had a bit of a baseline. And when they switched on the transformer and they first energized it, what they saw was dramatic. Within the first 6 hours, fault gases started appearing at a significant rate. So, for example, in this top plot here in green shows the hydrogen increasing from 0 to about 100 ppm over the course of a day. But also down below that is acetylene, which increased from 0 to about 6 ppm over the course of the day. And you can imagine here, we got the call on this unit right around here when the acetylene had reached 2 ppm. So this was a case where this very sensitive fault detection, well, it's a multi-gas monitor, so very sensitive multi-gas monitor was able to pick up early fault in acetylene when it was less than a couple of ppm. So this turned out to be a happy story for the owner. They de-energized and they did a bunch of other diagnostic tests, and ultimately the OEM was called in and they did a teardown, and the transformer was returned to the manufacturer under warranty. So the fact that this monitor was there giving this timely data prevented a lot of cost and a lot of risk to that operator. So I think we're doing reasonably well here on time. This is my last slide. So a couple of points to touch on here. Some of them I mentioned already. If we think about factors that are important to ensure a good return on investment, the first of the list is really set those alarm levels based on the history of each individual transformer. If you're not sure what that means, or you want some guidance as to how to do that, we're happy to help. We have a kind of a recommended process for doing that. It's really a low-cost way to ensure you're getting the maximum value out of your DGA monitors. The other one is even more basic. It's simply to connect the communications back to the SCADA, or back to the data analysis software. It's surprising the number of times that the asset management team and the IT team, they just can't quite agree on how to or if to connect the monitors. And so there are people out there with monitors not connected, just running on their own. So that obviously is not a great way to maximize the early fault detection from the monitors. Another point that people have come back to us time and time again is, it's really helpful to practice what to do if there's a gas alarm on a monitor. If people know who should do what, I mean, these are typically a little bit stressful times if you know you've got a gassing unit, especially a critical unit. So it's very helpful to have rehearsed and practiced how people are going to react to that situation. From my point of view, let me talk about this for a bit. From my point of view, fault detection monitors are a really excellent way to monitor more transformers within a budget. They provide really excellent early fault detection. The products themselves are simpler, they're less expensive, they're probably more reliable. So especially for people who are first embarking into DGA monitoring, and you want to develop a process, you want to build confidence in your company that this is a good way to go, I think it's really helpful to start with fault detection monitors, get some success under your belt, maybe save a transformer or two, and grow from there. So the idea of starting small and starting simple and gaining experience is a theme that's come back to us many times from people who have been successful, especially if their first attempt was not this and they were unsuccessful. So it's a very useful approach. That being said, there is a very strong growing interest in the use of multi-gas monitors, especially on high-value assets in critical applications. These monitors do provide more information. They can be just as good at early fault detection. They tend to require a little bit more investment of time and energy to keep a fleet like that up and running, but they can do things that we couldn't imagine doing, even 15 years ago. Simple things also, all monitors do require a small amount of maintenance. It's worth to keep up with that so that you're sure that the monitor is going to do its job when you need it. And then I mentioned already the importance or the advantage, let's say, of looking at your choice of monitor and your choice of vendor as a long-term partnership, which will benefit both parties over the long haul. So that was my last slide. And thank you again for your interest and for your attending. I think we're kind of reaching the end of we're past the end of our time, so I probably should best let you go. I will go through the rest of the questions afterward. Thank you in advance. Thank you for all the questions and all your interest. I do appreciate it. It's been a pleasure to have the opportunity to share these messages with all of you today. So, thank you very much for your attendance.